Hello, today we're continuing in our series on quantum mechanics concepts, looking at the subject of electron spin. So far we've considered polarization of photons, now we're considering the spin of an electron. We can think of an electron spin for these purposes as a tennis ball spinning. Now a tennis ball which is spinning will spin around an axis. It can spin around any axis and it can spin at varying speeds. So if we draw our tennis ball, we can say that it will spin on an axis, which could of course be an axis in any direction, and in spinning it will spin at a certain angular speed omega radians per second, and it will have an axis of spin. And that means that we can replace this whole description simply by drawing the axis. And the arrow indicates is an indication of spin by virtue of the corkscrew rule. You simply say if the corkscrew is pushing in this direction, then you would have to turn it clockwise in that way in order for the corkscrew to go in. Therefore the tennis ball or the electron is spinning clockwise in order for the corkscrew to move in that direction. Therefore the axis is shown by the line and the arrow gives you an indication of which way the spin is going. Now that turns out to be not a bad model for electron spin, except in one respect. I said that a tennis ball could rotate at varying speeds. When it comes to an electron, there is no such notion of varying speeds of spin. The electron just has spin. Furthermore, it turns out that when you come to measure an electron spin, which could of course be in any direction, you can only measure it against one coordinate axis. So we can think of a machine rather like the one we used for polarization, but this time it's got different electronics in it. It has an arrow which indicates the angle or the coordinate direction that you're measuring the spin against. It has a red light and a green light, just as we had before, which will indicate whether or not the spin is measured as up or down according to this direction. Irrespective of this direction, it will simply measure up or down according to the direction of the equipment. And that's what we're going to be looking at. So now I want to tell you some experimental results. Here is my equipment, which of course I could point in any direction. I can turn this equipment round if I want to, but for the time being I'm going to keep it in the upwards direction, and we're going to have the frame of reference we're going to use is that up is going to be the Z frame of reference. The, as it were, left-right is going to be the X frame, and the in-out is going to be called the Y frame or coordinate. So we are measuring along the Z coordinate, which for our purposes we will regard as up or down. Now this is an experimental result. You can prepare electrons with their spin in a certain direction. It basically involves passing them through a magnetic field so that all the electron spins, no matter what they were previously, align such that they are aligned in any direction of your choosing. In this case, I'm choosing to align them up. They are completely up on the Z-axis, and we're going to put them through my measuring machine, which is going to measure them along the Z-axis. And what that machine will tell us is whether the electrons are spin up or down according to that axis. And you perhaps won't be surprised to know that experimentally you will determine that 100% will come out as measured up, because they are all up against the Z-axis. So that's not a particularly surprising result. If on the other hand I prepare my electrons such that they are all absolutely spin down along the Z-axis, you perhaps won't be surprised to know that 100% of them will come out spin down. So let's just be sure we understand what's happening, because it's crucial to what happens. We've got a machine that's got a red light and a green light, And the whole point is that there is some electronics in this machinery here which will measure the spin of an electron against the axis of the arrow. As I've said, you can turn the equipment if you want to, and it will always measure the spin of the electron in the direction of the arrow, and it will give you one of two results. It will either say that the spin is up in the direction of the arrow, or it is down in the direction of the arrow. That's the only result you can get from this piece of equipment. And what I'm saying is, when you prepare the electrons such that they are all spin up against the z-axis, and you measure it against the z-axis, every single one of those electrons that goes through that piece of equipment will cause the red light to come on, which indicates that they are spin up. If you prepare your electrons spin down, every single one of them passing through that equipment will cause the green light to come on, which means they are spin down. But now, suppose I prepare my electrons with their spin in this direction. What will happen? Well, you might argue that an electron with a spin in this direction has two coordinates. It has an up coordinate, because there is essentially an up direction, and it has a right coordinate, because there is essentially a coordinate that's pointing to the right. There is no down coordinate. Clearly, this is essentially pointing a bit up and a bit right. And therefore, you might argue that when you put these electrons through this device, which is measuring against the z coordinate, that it should essentially simply measure that this is effectively an up direction, and consequently you would expect to get 100% of those coming out as up. But what you actually find is, and it depends on the angle but you'll find sort of 80% will come out up, but there will be 20% of those electrons that are at this angle passing through this machine that will cause the green light to come on, indicating that they have been measured as spin down. Similarly, if you prepare your electrons such that they are pointing in this direction, again you might conclude that they are all essentially spin down and a little bit of spin right, but you'll find amazingly that 80% of them will come out spin down, which is what you'd expect, but you might well get 20% of them that will be spin up. So the peculiarity, and this is an experimental result, that even though you have prepared the electrons so you know that they are pointing in this direction, when you put them through a device that is measuring whether or not they are up or down, a large proportion of them will be registered as spin up, but a small proportion of these will be registered as spin down. Now, this is again the weirdness of quantum mechanics. All of these electrons are absolutely identical. They have all been prepared with their spin in exactly the same direction, and yet some of them are registered as up, most of them in fact, but some of them as spin down. And if you prepare them such that their spin is entirely along the x-axis, so there is no up and there is no down coordinate at all, you might expect that when you put these electrons through a measuring device in the z direction, neither the up nor the down light would come on. But in fact what you find is when you put these electrons one at a time through this piece of equipment, 50% of them will give you an up and 50% of them will give you a down. So even though there is in essence no up or down coordinates to electrons which are essentially pointing to the right along the x-axis, when you put them through this equipment, you will find that half of them will come out as up and half of them down, and there is no way of predicting which one will be which. So now if we try to represent what we've just learned in our Dirac notation, we would say that if you have an electron whose spin is prepared in this direction, then what we've learned is that some of those electrons will give a spin up. Don't forget, our measuring device is always measuring for, at least for the time being, I'm always going to be measuring in the z direction, no matter what the angle of the electron. So the electron spin is prepared in this direction, but I'm always measuring it against the z-axis, and I want the result, is it going to be up or is it going to be down? And what we found is when you put electrons all prepared in this direction through this device, most of them come out up, but some of them come out down. And so what we can say is that we can represent that spin in this way: alpha up plus beta down. What do we mean by that? We mean that there's a bit of up and a bit of down inherent in this spin, because sometimes the electrons will give an up and sometimes they will give a down. And what have we already learned about these values, alpha and beta? They are the probability amplitudes of getting an up or a down. And remember, to get the probability, you have to square these terms. Or more accurately, what you can say is that the probability of getting an up is equal to alpha times its complex conjugate. Remember, whenever you square anything, what you actually mean is multiplying that number by its complex conjugate. And similarly, the probability of getting a down is going to be beta times its complex conjugate. And since you must get one or the other, since those are the only two options, it's either up or it's down, it must be true that the probability of getting an up, which is alpha, alpha star, plus the probability of getting a down, which is beta, beta star, must equal 1. Because you must get one or the other. So the total probabilities must sum to 1. And now, in a sense, we've learnt something else about this kind of equation. We know that alpha and beta represent the probability amplitudes of getting up or down. But we also now know what up and down essentially are. They are what's called basis vectors. They are, when we say basis vectors, we mean they're orthonormal. What we mean is if you are up, you are definitely not down, and if you're down, you're definitely not up. So in this case, we've only got two basis vectors because there are only two options. It could be up or it could be down. There is no other option as far as this equipment is concerned. Those are the only two results you can get. And what this is called is a linear superposition of states. That is to say that that electron is, as it were, born with this linear superposition. It has a probability amplitude of being up and it has a probability amplitude of being down. And it's not until it actually gets to the equipment that nature makes a choice and decides whether it will be registered as up or down as it goes through the equipment. So let's just take this general form and see what we can deduce from some specifics. For example, we know that if we prepare the electron such that it is completely spin up in the z direction and we measure it in the z direction, 100% will come out measured as up. So therefore we can say we know the spin state of this. It's simply going to be 1 up plus 0 down, because the probability of getting an up is 100%. 1 squared is 1. The probability of getting a down is 0%. 0 times 0 is 0. Similarly, if we prepare the electron completely spin down in the z-axis and we measure it, as always, against the z-axis, we know that we're going to get no chance of getting an up and 100% chance of getting a down. We also found that if we prepared the electron along the x-axis, that there was a 50% chance of getting an up and a 50% chance of getting a down. And that means you have to, and if you remember, it's 1 over root 2 up and 1 over root 2 down. Why is it 1 over root 2? Because you have to square these terms to get the probability. So the probability is going to be 1 over root 2 squared, which is a half, which is 50%. And the probability of getting a down is also going to be 1 over root 2 squared, which is a half, which is 50%. Now, I've already referred to my equipment, which is a piece of equipment which measures the electron spin against an axis and gives you an up or down. That means it goes in the direction of the arrow or in the opposite direction of the arrow as measured through this equipment. But of course I can turn that equipment, as I've already said, in any direction I like, and it will always measure the upness or the downness of the electron spin according to that particular alignment. But of course there are three coordinates that I could use, and we've already spelt them out, the Z, X and the Y. The Z is the up and down coordinate, the X is the right-left coordinate, and the Y is the in-out coordinate. I could of course point my equipment in any direction I like, but those are, as it were, the three Cartesian coordinate directions that I could choose. So we're going to start by considering those. So I need an operator that will give me an up or down measure. I'll need one that gives me a right or left measure, and I'll need one that gives me an in or out measure. And you'll remember that operators are matrices. And thinking back to when we did polarization, we found three specific matrices. And I'll just write them down. We had the 1, 0, 0, -1 matrix. That, if you'll remember, was when we were measuring polarization either in the horizontal or vertical direction. We had another one that was the 0, 1, 1, 0 matrix. That was the one when we were measuring polarization in the backslash or forward slash directions at 45 degrees. And we had the 0, I, 0 matrix. That was when we were measuring circularly polarized light either in the clockwise or the anti-clockwise direction. And the question is, I wonder if these three matrices might also have a use in measuring the electron spin. And guess what? It turns out that they do. I will illustrate later on why that is the case, but just for the moment I'm telling you that these three matrices that we developed for the purposes of polarization of photons can also be used for electron spin. Indeed, it turns out that these three matrices, which are called Pauli matrices, have an enormous value in quantum mechanics and indeed in particle physics. And what do they actually represent? Well, I'll rub out what was appropriate for photon polarization, because now it turns out that this is the operator you use for up and down, this is the operator you use for right and left, and this is the operator you use for in and out. This is called the sigma Z matrix, sigma Z, because it measures along the Z axis. This is called the sigma X matrix because it measures along the X axis, which will now be right or left. And this is the sigma Y matrix because it measures along the in and out of the board. And of course they're going to have exactly the same eigenvectors as before. You'll remember that the eigenvectors of the two eigenvectors that came out of this matrix were 1, 0 and 0, 1. And that now represents up and down. And it will have eigenvalues of +1, -1. Essentially, these represent your red and your green lights. If the red light comes on, it means you've measured an upspin, which means it's in this state. If you get a green light, it means you've measured a downspin, which means it's in this state. The eigenvectors for this matrix, you may recall, were 1 over root 2, 1 over root 2, and 1 over root 2 minus 1 over root 2. And they now represent right and left. And once again, you get eigenvalues of +1 and -1. The red light comes on, it means the spin is to the right. The green light comes on, it means the spin is to the left. And over here, you may remember that the eigenvectors were 1 over root 2 and I over root 2, where I is the square root of -1. And the other one was 1 over root 2 minus I over root 2. And that is now going to measure in, and this is going to measure out. And once again, the eigenvalues are +1 and -1, the red and green light telling you whether it's in or out. So you'll remember from photon polarization we developed a rather important formula. We had an operator H, which is a Hermitian matrix, acting on a state, which I'm now going to introduce the Greek letter psi for, and that produces a number, a real number, multiplied by the same state psi. Psi starts to become a generic term for the state of a system. And this has continuing applicability to what we've just learned. The Hermitian operator is one of the three matrices that we've just identified, the up, down, right, left, in, out. The psi eigenvector is one of the two eigenvectors associated with each of those matrices. And lambda will be +1 or -1, which in a sense is the red light or the green light on our equipment, that tells us whether the equipment has actually identified an up state or a down state, or a right state or a left state, or an in state or an out state, depending on which of the operators we use. We also learned another rather important concept. This is called an inner product. It's the inner product of alpha with beta. And what it says is that if you prepare a system in state alpha, what is the prospect of measuring it in state beta? And that is the probability amplitude. If you want the probability, you have to square it. And remember, whenever we say square, we actually mean you multiply by its complex conjugate. So let's try it. Let's suppose we prepare in the up state, that is to say, we prepare the electron in the z-axis, pointing upwards. What is the prospect of measuring a right? That means that our equipment is going to be pointing in the right direction. And it will give us either a right or a left. Either the red light will come on or the green light will come on. And this is the question. If we prepare it in that state, we measure it in that state, what is the prospect of getting a right, obviously, as opposed to a left? And we know how to do that. You simply take the two eigenvectors and you do the inner product. For the bra vector, you use a row vector, and that you may remember we said that right was 1/√2, 1/√2. You should complex conjugate this because it's a bra vector, but actually there is no imaginary term, so there's nothing to do. And the upturn becomes 1 and 0. And so you simply have 1/√2 times 1 plus 1/√2 times 0 is 1/√2. And that's the probability amplitude associated with preparation in the up direction and measuring in the right direction. If you want the probability, as I've said, you have to square, which means you have to square this, which means you have to square this, and 1/√2 squared is 1/2. And that's exactly what we would expect if you prepare in the up direction and you measure in the right direction. There's a 50% chance that you'll get a right, and there's a 50% chance that you'll get a left. Let's do another one. Let's, for example, say that we prepare in the left direction and we want to know what is the probability of measuring an in the in direction. And remember, the probability is this squared. So this is essentially you prepare the electron in the left direction, and then you're actually measuring it with a piece of equipment which is now pointing into the board. So we show that by a cross, it's pointing into the board. So essentially we want to know, if you prepare in this direction and you put it through this equipment, what is the probability that we will get an in as opposed to an out? Well, once again, we have to take the bra vector of the in, which you may remember was 1/√2 I/√2. But hang on a minute, for the first time, we've now got the problem that we've got to complex conjugate that, because we have now got an imaginary term. How do you complex conjugate? you'd simply change the sign of the imaginary term. So this now becomes minus I over root 2. And we multiply by the left eigenvector, which you may remember was 1 over root 2 minus 1 over root 2. And that will all have to be squared, or more accurately multiplied by its complex conjugate. Well, what is that going to come to? You've got 1 over root 2 times 1 over root 2 is a half. And then you've got minus I over root 2 times minus I over root 2, which is going to be plus I over 2. And now we've got to square that. Or, I'll say it again, you have to multiply it by its complex conjugate. So that's 1 over 2 plus I over 2, multiplied by its complex conjugate, which is going to be 1 over 2 minus I over 2, because you simply change the imaginary term. Now you'll notice that the products of those two are going to balance the products of those two. Those two multiplied together will balance those two multiplied together. So all you're left with is a half times a half, which is a quarter. And I over 2 times minus I over 2 is minus I squared over 2. Sorry, minus I squared over 4. But minus I squared is plus 1, because I squared is minus 1. So you've now got plus another quarter, and that gives a half. There's a 50% probability, and that's exactly what we would expect. If you prepare the electron in the state where it's pointing left, and you measure it along the in or out axis, you would expect that half of them would measure in and half of them would measure out. So let me labour the point again. We're using this famous equation that the Hermitian operator, one of the three matrices we've developed, acting on one of its eigenvectors, in this case there are only ever two, give you a number multiplied by the same eigenvector, and the numbers always turn out to be either plus 1 or minus 1. What that means is that you've got an electron that is prepared, let's say in this state, at a certain angle to the vertical. And what we've said is that that state of that electron contains a superposition of ups and downs. There's a little bit of up and there's a little bit of down in the state of that electron. It means it has the capacity to be measured as up along the z-axis, or it has the capacity to be measured as down along the z-axis. So when you put it through our piece of equipment, which is measuring along the z-axis, you've no way of knowing whether nature will determine that this will be up or down. But it will give one or the other with the probability amplitudes alpha or beta, and the probabilities of course are alpha squared or beta squared. And I remind you that alpha and beta are the probability amplitudes, and the states up and down are the basis of states. You need what's called a complete basis to describe this eigenvector. A complete basis of states, in this case there are only two. When you are measuring in this direction, when you are using the, as it were, the sigma z Hermitian operator, there are only two outcomes you can get, up or down. And therefore up and down are the complete set of basis vectors. And for each of them there is a probability amplitude. But here's the weirdness, and I repeat it. If you prepare 1,000 electrons, all with their spin in this direction, and you put them through this piece of equipment, you'll find most of them will give spin up, but some of them will give spin down. The weirdness, of course, being they are all exactly the same. They all have the same spin direction. They are all electrons, and yet when you put them through this device, some of them come out up and some of them come out down. And who decides? Well, certainly not me, and certainly not the equipment. Nature somehow makes the decision that even though the state of that electron is a little bit of up and a little bit of down, when it goes through my measuring device, it has to make a choice. And so therefore it chooses either to be up or to be down. But here's a further element of weirdness. This is my electron, just one electron. It has this state, a little bit of up, a little bit of down. You take it and you measure it in my device. That device will give you a result, either up or down. Let's suppose, just for a moment, that on this particular occasion, this electron is measured as spin up when it goes through the measuring device. Something else happens. And what happens is that electron spin itself will now be spin up. It was at this angle. It goes through this device where it might be measured as up or down, but when it comes out, if it has been measured as up, the electron spin itself will now be wholly up. If it had been measured as down, the electron spin would be wholly down. So here you've got a further weirdness of quantum mechanics, that when the electron which has a spin in this direction is measured, the effect of measuring changes its state. It measures it as up and it collapses. It's what's called collapse. The state collapses to up. So in this stage, it was a bit of up and a bit of down. But once it's been measured as up, it is entirely up and beta falls to 0. And alpha, of course, becomes 1. It now has a complete state of up and no state of down. And that was the consequence of measuring. So now I want to consider an electron whose spin is at an angle theta to the vertical, being measured by a device that is measuring along the z-axis, where again there are only two possible outcomes, up and down. And I want to know what is the probability of measuring an up or a down. Now you might say, we know the answer to this. This is analogous to the problem we had with photon polarization, where the probability was given as the probability of an up is cosine theta. That's what we had. In fact, it's cosine squared theta. The probability amplitude would be cosine theta, so that when you square it, you get cosine squared theta. So we know that. Well, I'm afraid that's not going to work. It's fine when theta is 0, in other words, when the electron is aligned against the z-axis, you know that there's a 100% chance of it being measured as up. Well, the cosine of 0 is 1, so the probability amplitude when the electron is spin up is going to be 1, and therefore the probability of an up is going to be 1 squared, which is 1. That's fine. But what happens if the electron is at 90 degrees to the up? We know that if you prepare an electron along the x-axis and put it through this piece of equipment, there's a 50% chance of getting an up and a 50% chance of getting a down. But when theta is 90, the cosine of theta is 0. So the probability of getting an up would be 0, and that's wrong. It has to be 50%. So we have to change our probabilities just a little bit, and we find that the probability amplitude, the probability of getting an up amplitude is cosine theta over 2. And then the probability itself will simply be cosine squared theta over 2. And that's going to work, because now when theta is 0, in other words, when you align it against the z-axis and measure it against the z-axis, you're going to get cosine of 0, which is, of course, 1. And theta is 0, which means theta over 2 is 0. And the cosine of 0 is 1, so cosine squared is 1. That's fine. When the electron is at right angles, in other words, travelling along the x-axis, theta is 90 degrees, theta over 2 is 45 degrees, cosine theta over 2, cosine of 45 is 1 over root 2, so cosine squared is 1 over root 2 squared, which is a half. That works. So now we can write that the state of an electron which is prepared at an angle theta to the vertical, the state will be a bit of up and a bit of down. And what are the probability amplitudes? Well, the probability amplitude of up we've just given. It's cosine theta over 2. And what is the other one? Well, it's sine theta over 2. Why? Because those two added together when squared must give 1, because the probabilities added together must equal 1. It must be one or the other. So you've got the situation that cosine squared theta over 2 plus sine squared theta over 2 equals 1. And that's why, and you have to have, if you've got cosine squared plus something equals 1, it has to be plus sine squared to get 1. And so the probability amplitudes respectively are cosine theta over 2 and sine theta over 2 for an electron that has been prepared with a spin at an angle theta to the vertical. Now at this point I just want to draw your attention to some of the what one might call uncertainties associated with quantum mechanics. For example, suppose I were to prepare an electron, I do it, and I tell you that I have prepared it either in the state pointing straight up or in the state pointing to the right. I know which one I've done, but I don't tell you. I simply say to you, can you perform a measurement that will always and unambiguously identify which of the states it's in? It's in one of those two states, but I haven't told you which. Well, let's have a think about what you might do. The two most obvious experiments that you can make are either to measure along that axis or to measure along this axis. You can only do it once, remember, because as soon as you make the measurement, the spin will collapse into the measured state. So you can't do this and then this, because that's not going to work. You have to do one or the other, and it's your choice. Now, if the electron had been prepared in this state, then there's a 100% chance of you getting an up measurement, because it's in this state and you're measuring it in the same direction. You're definitely going to get an up. But if I had prepared it in this state and you put it through that equipment, then there's a 50% chance of getting an up and a 50% chance of getting a down. What happens if instead you choose to do the experiment with the equipment pointing in this direction? Well, if it were up, then you will find that there's a 50% chance of getting an up or a down, which in this alignment means a 50% chance of getting an up in this direction is to the right, a down in this direction is the equivalent of left. Whereas if I had prepared it in this direction and you put it through this piece of equipment, you will definitely get 100% right. So here's the point, that you don't know which of these two is the case. So if you choose to measure with the equipment pointing in the Z direction, it's perfectly plausible that you could get an up for either of them. And if you were to use the equipment in this direction, it's perfectly plausible that you would get a right for either of them. And if you get up, if you do it this way, or you get right if you do it this way, you cannot tell me which way the electron's spin was prepared, because both of them could give you the same result. But if you are lucky enough to get a down if you do it that way, or a left if you do it this way, now you can say for certain, if you get a down having measured this way, you know the electron must be prepared to the right, because if it had been prepared up, you could never get a down. Similarly here, if you get a left, you know that the electron must have been spin up, because if it had been prepared spin right, it could never have given a left. So you might get lucky. If you put the electrons through the equipment, and remember, you don't know which way this spin is. If you get a down, having chosen that particular alignment, then you can say for certain that the electron was prepared spin right. Alternatively, if you use this equipment and you get a left, you can say for certain that the electron was spin up. But if you get, as a result of this experiment, you get an up, that tells you nothing. And if as a result of this experiment you get a right, that tells you nothing. So you cannot always and unambiguously determine which of these two states I prepared the electron in. But you can get lucky. If you get the right results, then you can unambiguously tell me which state I prepared it in, but you cannot guarantee to do so. So now I've written up on the board the linear superposition of different states. Up is definitely up, 1 up plus 0 down. Down is definitely down, so it's 0 up plus 1 down. Right can be described as 1 over root 2 up plus 1 over root 2 down, which means the probability is the square of this, a half and a half of getting up or down. Left is the superposition of 1 over root 2 times up minus 1 over root 2 times down. Once again, the probabilities of up and down are the squares of these amplitudes, half and a half. The in state can be represented as 1 over root 2 up plus I over root 2 down. And the out state is represented as 1 over root 2 up minus I over root 2 down. And remember, for these two states, where you've got imaginary terms, when you square them, you always have to multiply by the complex conjugate. So this is I over root 2, the probability would be I over root 2 times minus I over root 2, which is, of course, minus I squared over 2, and minus I squared is 1. So it's 1 over 2, which is a half. But you'll notice that what we've done is we've expressed all these states in terms of ups and downs. So essentially we have elected to choose up and down as what we call our basis states. Those are our fundamental states in terms of which everything else is expressed. And remember, you have to have a complete set of basis states. So in this case there are only two. It can be up or down. Later we shall find that you need more than two. Indeed, in some cases you need an infinite number of basis states. But these are the basis states. But you didn't have to choose up and down, I just did. But you can actually express any of these states in terms of any other. For example, let's take these two equations here which relate to right and left, and let's add the two together. So if we add right and left, you get right plus left is equal to, well, here you've got 1 over root 2 up plus 1 over root 2 up, which is 2 over root 2 up. And here you've got 1 over root 2 down minus 1 over root 2 down, so that cancels and goes all together. So here you've now got right plus left equals 2 over root 2 times up, and 2 over root 2, of course, is simply root 2. If I divide both sides by root 2, then that goes. And now I've got up expressed in terms of right and left. So I originally had right expressed in terms of up and down, because that was the way I chose to do it. But you could, if you wish to, use right and left as your complete set of basis vectors, and then you can express everything else in terms of right and left. In this case, I've just calculated it for up. Up would be right plus left divided by root 2. Okay, so now I think I owe you an explanation of where those matrix operators sigma x, sigma y and sigma z come from. Now we've got to start somewhere, so I'm going to be taking my starting point that if I prepare an electron in the spin up direction and I put it through my measuring device, which is also measuring along the z axis, I know that 100% of those will come out spin up, and were I to prepare the electron spin down, I know that 100% of those would come out spin down. So I can start, my starting point is simply to assign that my up eigenvector is going to simply be represented by the combination of states of 1 up plus 0 down, and my down state is simply going to be represented by 0 up plus 1 down. And that means that my up state is essentially 1, 0, and my down state is in column vector terms 0, 1, because you simply take the probability amplitudes. Here it's 1, 0, and here it's 0, 1. And that is essentially my starting point. So thinking about the sigma z, the matrix operator that operates along the z-axis, we know what it is because I've told you, but let's suppose you didn't know. And let us suppose that it's an A, B, C, D. You know it's got to be a 2 by 2 matrix because we know that the eigenvector on which it's going to apply is 1, 0. The other one, of course, being 0, 1. But let's start with the 1, 0. I'm going to require that these produce eigenvalues of 1 and minus 1. That's my choice, but I'm allowed to do that. And of course, if this is right, if this is Hermitian operator acting on an eigenvector, it will give me an eigenvalue, which I want to be plus 1, times the original eigenvector. And I also know that the same operator acting on the other eigenvector, which is the 0, 1, the down eigenvector, will give me a minus 1 times the same eigenvector. Well, now I can work out in each case what that amounts to, because I know how to do a matrix operation on an eigenvector. So what do? We take A times 1 plus B times 0. So A times 1 plus B times 0 is going to be equal to this top number here, which is plus 1. And from that you should immediately see that A must equal 1. Because 1 times 1 plus B times 0 equals 1. What about here? C times 1 plus D times 0, C times 1 plus D times 0 is going to equal plus 1 times 0, which is equal to 0. Well, in those circumstances, C must equal 0 or 0, because 0 times 1 plus D times 0 is 0. Now let's come down to here. A times 0 plus B times 1, A times 0 plus B times 1 is going to be equal to minus 1 times 0, which is 0, in which case B must equal 0, because A times 0 plus B times 1, well, B has to be equal to 0. And then finally C times 0 plus D times 1, C times 0 plus D times 1 is going to be equal to minus 1 times 1, which is minus 1. And therefore you can see that D must equal minus 1, because C times 0 is 0, and then D times 1 is minus 1. So I now know what my values are. I can remove this here, and for A I can put 1, for B I can put 0, for C I can put 0, and for D I can put minus 1. And that is the sigma z matrix, derived, if you like, from the starting assumption of my eigenvectors 1, 0, 0, 1, and saying that I want my eigenvalues to be plus 1 and minus 1. Now I can remind you that if I have an electron prepared with spin up, and this time I measure it in the device that is pointing right and left, which of course is the sigma x matrix, that's the one that looks along the right and left way, I know that I will get a 50% chance of it being up, which is essentially right, and a 50% chance of it being down, which in this case is left. So it's definitely spin up because I prepared it that way. When I put it through this device, it will give me a reading of either up in the direction that the arrow is pointing, which is right, or down in the direction the arrow is pointing, which is left. And it's a 50% chance. As we've already said, right is 1 over root 2 up plus 1 over root 2 down, where these are the probability amplitudes, and left is 1 over root 2 up plus 1 over root 2, sorry, minus 1 over root 2 down. So the eigenvectors in this case will be 1 over root 2, 1 over root 2, and 1 over root 2 minus 1 over root 2. So now if I want to find my sigma x operator, let's call it again A, B, C, D. I'm now acting on, well, let's take the first eigenvector, which is 1 over root 2, 1 over root 2, and that's going to have to produce an eigenvalue of plus 1 times 1 over root 2, 1 over root 2. And the other is taking the same matrix, A, B, C, D, but acting on the other eigenvector, which is 1 over root 2 minus 1 over root 2, to produce minus 1 times the same 1 over root 2 minus 1 over root 2. And now I can multiply just as I did before, but we're going to get a lot of over root 2's. In fact, every time we multiply, we're always going to get an over root 2. So I'm just going to leave all the over root 2's out because they will cancel on both sides of the equation. So we're going to get a times, I'm just going to look at the numerators of these fractions. A times 1 plus b times 1 equals 1. So a times 1 plus b times 1 equals 1. Right? I could have said a over root 2 plus b over root 2 equals 1 over root 2, but then I could cancel root 2's in each case. So let's save time. And then I've got c times 1 plus d times 1, which is just c plus d, is equal to 1. From here I've got a times 1 minus b times 1, so that's a minus b equals minus 1. And here I've got c times 1 plus d times minus 1, so that's c minus d, is equal to minus 1 times minus 1 is plus 1. Let's take this equation here and this equation here and add the two together. A plus a is 2a, b minus b is 0, 1 minus 1 is 0, so 2a equals 0. That means a must equal 0. If a equals 0, it's pretty clear to see that if a is 0, b must equal 1. So b equals 1. Now we'll take this equation and add them together. C plus c is 2c, d minus d is nothing, 1 plus 1 is 2, 2c equals 2, c must equal 1. And then if c equals 1, it's pretty clear to see that d must equal 0 because 1 minus 0 equals 1. And so now we have the sigma x matrix derived. It's 0, 1, 1, 0. And finally we'll look at the sigma y matrix in exactly the same way as before. We're going to call that A, B, C, D. And we know the eigenvectors for the sigma y. That's 1 over root 2 and I over root 2. And we're going to require that that equals eigenvalue plus 1 times the same eigenvector. Or we can do it the other way using the sigma y matrix A, B, C, D times the other eigenvector, which is 1 over root 2 minus I over root 2, and that's going to become minus 1, the eigenvalue, times 1 over root 2 minus I over root 2. Once again, all of these terms have got root 2's in them, so we can cancel those out, make life easier. We've got, just looking at the numerator, a times 1 plus b times I, so that's a plus bi, is going to equal 1 times 1, which is 1. Here we've got c times 1 plus d times I, so that's c plus di, is going to equal 1 times I, which is I. Here I've got a times 1 minus bi, so that's a minus bi, is equal to minus 1 times 1, which is minus 1. And here we've got c times 1 minus di, so that's c minus di, is equal to minus 1 times minus I, which is plus I. Once again, as before, we'll take those two equations and add them together. So a plus a is 2a, bi minus bi is 0 and 1 minus 1 is 0. So I've got 2a equals 0. That means that a must equal 0. And if a equals 0, that means bi equals 1, which means b has to be equal to minus I. Because if b is minus I times I is minus I squared is minus 1, so minus I squared is plus 1. What about these two equations? Add them together. C plus c is 2c, di minus di is nothing, I plus I is 2i, 2i equals 2c, which means that c must equal I. And if c equals I, then pretty clearly this term here must equal 0, because if c equals I equals I, this term is 0, which means that d must be 0. And so there you are, the third matrix developed and demonstrated on the basis of everything just fell out of the starting point of the up and down eigenvectors and everything that follows on from that. And just to remind you what this actually means is if you take an electron with spin up, or indeed any spin, the sigma z operator is the equivalent of measuring the spin against the z-axis. The sigma x operator is the equivalent of measuring the spin along the x-axis, and the sigma y operator is the equivalent of measuring the spin into the board along the in-out axis. But what happens if I take my electron and I happen to want to choose to measure it against any old angle, where not only is this an angle that is twisting in the plane of the board, but it can actually be twisting out of or into the board. It's a three-dimensional arrangement here. I can twist it in the plane of the board, but I can also twist it in or out. Well, essentially, I'm going to have this device here can be represented by a vector, which I shall call n. And that vector will have three components. It will have an nx component, an ny component, and an nz component along the three axes. This is the z-axis, this is the x-axis, this is the y-axis. If you drop perpendiculars to each of those axes, then you will get the, as it were, the n component, the nx component, the ny component, and the nz component. We know that the vectors are always of length 1, so by Pythagoras we can say that nx squared plus ny squared plus nz squared is 1. Because that has always been the case, and we might as well require it to be the case now. And what we can say, or at least what we can try and say and see if it works, is that since we've always been talking about linear superposition, this should mean that you should be able to add the operators because they are linear operators, so you can add them. And what that essentially means is that you can regard this operator as a linear combination of all the three operators that we have currently developed. And what we're going to say is that the value of each operator is to be multiplied by nx, ny and nz, representing that bit of the component that is in that direction. So in other words, what we're saying is that this operator can be represented as nx times sigma x plus ny times sigma y, these are of course operators, plus nz times sigma z. And that will be essentially the operator n, where n is this particular angle, which, don't forget, may have an in or out of the board element. So this means that sigma n, the operator for the equipment that is pointing in the n direction, which has coordinates nx, ny and nz, will be the linear superposition, which is nx times sigma x, and sigma x is 0, 1, 1, 0, plus ny times the sigma y, which is 0 minus I 0, plus nz times sigma z, and sigma z is 1 0 0 minus 1. And that means that sigma n is going to just become a ginormous matrix. It's still going to be 2 by 2, but we're going to have to do the superposition of all of them. So let's think about the top left-hand corner. Well, there's nothing, nx times nothing, ny times nothing, and nz times 1. So you're just going to get an nz up here. Top right-hand corner, we're going to get an nx minus an nyi. So this is nx minus nyi. Bottom right-hand corner, we're going to get an nx. We're going to get a plus nyi, but nothing here. And then the bottom right-hand corner, nx times nothing, ny times nothing, nz times minus 1 is minus nz. So that is my sigma n operator. That is as far as you can go unless you know the respective values of nx, ny and nz. But you will notice that this is a Hermitian operator. If you reverse these two and complex conjugate, you get the same thing. nx plus nyi going up here, change the sign, becomes nx minus nyi. So it is Hermitian, it will work. So what we now know is that if it's Hermitian and it's an operator, it will become an experimental measurable. And if we act on some eigenvector, which for the moment I will call alpha beta, that will produce an eigenvalue lambda times the same eigenvector alpha beta. And I am going to require, at least, that just as with all the other ones, that the eigenvalue is plus 1. So now I need to find what this eigenvector is. Now I can, without loss of generality, say that the alpha beta, I can regard that as 1 gamma. The reason I can do that is that that will have to be normalized anyway, because remember that the eigenvector times its complex conjugate must equal 1. Total sum of probabilities must equal 1. So I'm going to have to normalize this anyway, so it doesn't really matter if I change it from alpha beta to 1 and gamma, because I will then have to find out what the normalization factor is. But first, let's see if we can work out what gamma is. So we take sigma n, which you'll remember was nz, nx minus I ny, nx plus I ny, and minus nz. And we're going to act on the eigenvector 1 gamma to give us plus 1, because that's the eigenvalue, times the same eigenvector 1 gamma. Well, we actually only need to do the top line. nz times 1 is nz, plus nx minus iy times gamma, is equal to plus 1 times 1 is 1. I can now say that nx minus I ny gamma is equal to 1 minus nz. All I've done is to take this nz and put it on the other side and change sign. And then I've got that gamma is equal to 1 minus nz divided by nx minus I ny. So I found gamma. Again, it's not very elegant because we don't know what the respective values of nx, ny and nz are. And so the total vector, 1 gamma, is now going to be 1, and then the bottom bit is 1 minus nz over nx minus I ny. But that probably isn't normalized. What we mean by normalized is that the eigenvector times its complex conjugate must equal 1. So what we're saying is that the eigenvector for sigma n is 1 gamma, and we've just worked out what gamma is. And we're also saying that psi times psi star must equal 1, which means that 1 gamma times 1 gamma must equal 1. Now I'm going to assume for a moment that it doesn't, and that it will need some normalization factor in front of it. And if we have a normalization factor, let's call it alpha, we have to put that alpha in front. That is not an eigenvalue, that is just a normalization factor that multiplies each of these terms, 1 and gamma. That's why I said it didn't matter that you put a 1 here, because in due course you're going to have to multiply it by the normalization factor. So in fact, alpha should be in front of that term and alpha should be in front of this term, which means you've got now alpha times alpha is alpha squared, and then this inner product is simply 1 times 1 is 1 plus gamma, and that of course is gamma star, so gamma star times gamma is equal to 1. Now we just have to put in the values of gamma star and gamma in order to find alpha. So we start with alpha squared into 1 plus gamma star gamma equals 1. That means that alpha squared into 1 plus. Now what was gamma? Gamma was 1 minus nz divided by nx minusiny. But remember that we actually have to do the complex conjugate of this, which means we have to change the sign of the imaginary term. There is only one imaginary term, it's here, so that becomes a plus. And that gets multiplied by gamma, which is 1 minus nz divided by nx minus iny. And that's got to equal 1. So that's alpha squared into 1 plus. Well, the top is just going to be 1 minus nz all squared. 1 minus nz times 1 minus nz. And at the bottom you've got nx times nx, which is nx squared, plus iny times nx minus iny times nx is 0. And then plus iny times minus iny is minus I squared ny squared. And minus I squared is plus 1, so that just becomes plus ny squared. Now I remind you that we showed that nx squared, or we said that nx squared plus ny squared plus nz squared equals 1 because the total length of the vector is always 1. And that means that nx squared plus ny squared, which is these two terms here, is simply 1 minus nz squared. So this term at the bottom simply becomes 1 minus nz squared. But I can factorise 1 minus nz squared into 1 minus nz and 1 plus nz. If you multiply it, you get 1 times 1 is 1, minus nz plus nz goes, and minus nz times nz is minus nz squared. And now 1 minus nz cancels one of those 1 minus nz's. I need a remaining bracket there. And now that's going to equal alpha squared into, for this 1, I'm just going to make this 1 1 plus nz over 1 plus nz. I can do that. Anything divided by the same number is 1. And then I'm going to add to that this term here, the remaining term, which is 1 minus nz over 1 plus nz. I've now got two terms over the same denominator. Oh, and of course I should have said that equals 1 and that equals 1. That's the whole point. The right hand side is always equal to 1. Now I've got 1 plus nz minus nz. That all comes to 2 over 1 plus nz. So this goes out and is replaced by 2 divided by 1 minus nz. Sorry, n plus 1 plus nz. Let's get that right. I've just left the equation at the bottom. This is an alpha squared. You can now see that alpha squared from this here is equal to 1 plus nz divided by 2, which means that alpha is equal to the square root of 1 plus nz divided by 2. So now we can say that the total eigenvector is equal to the normalizing factor alpha times 1 gamma. And for that we'll need to remember what those values were. So let's write them down. That means that psi, the eigenvector, is equal to alpha, which was 1 plus nz over 2, the square root thereof, into the eigenvector unnormalized was 1, and then at the bottom was 1 minus nz nx minus I ny. And that, we said, had an eigenvalue of plus 1. Now, without knowing what nx, ny and nz are, we can't go any more than that. This is just a very general term. But we can just check to ask what would happen if nz equals 1 and nx and ny both equal 0. Because under those circumstances, you are simply if nz is 1 and the other two terms are 0, then that of course is simply the eigenvector of the sigma z matrix. And we know what that is. The eigenvector of the sigma z matrix with an eigenvalue of plus 1 is 1, 0. Is that right? Well, if nz is 1, 1 plus 1 is 2, 2 over 2 is 1, the square root of 1 is 1. This is 1, well that's fine. And what is this at the bottom? 1 minus 1 is 0. Doesn't matter what the denominator is, well it's 0 anyway. So that gives you 0. What happens if nx is 1? Well, you know that the eigenvector for sigma x is that, 1 over root 2, 1 over root 2. So if nx is 1, but ny and nz are 0, you've got 1 plus 0 over 2, so that's the square root of 1 over 2, which is essentially 1 over the square root of 2, times 1, well that's okay, 1 over the square root of 2 times 1 is 1 over the square root of 2. And here you've got 1 minus 0 divided by 1 minus 0, so that's 1, times 1 over the square root of root 2. And that works as well. Now what happens if ny is 1, but x and nz are 0? Well, we know what the eigenvalue will be. It will be 1 over root 2 and I over root 2. Sorry, the eigenvector will be 1 over root 2 and I over root 2. Is that true? Well, nz is still 0, so it's 1 over root 2 square root, which is 1 over the square root of 2, times 1. Well, that gives us that, so that's okay. And here we're going to have 1 minus 0, so that's 1, divided by 0 minus I, because ny is 1. And 1 divided by minus I is plus I. And so since you're multiplying by 1 over root 2, you've got I over root 2. So that works as well. So when you look at that general formula and you reduce it to when only nz equals 1 and only nx is 1 and only ny is 1, then you get the eigenvectors for sigma z, sigma z, sigma x and sigma y respectively. Of course, you may then ask yourself the question, what happens if we prepare the electron in state M and measure it in direction n? Then what we're going to have to do to find the probability that something prepared in state M will give us an up reading in state n. You prepare it in state M and you measure it in state n. This inner product gives you the probability amplitude, and if you square that, or more importantly multiply it by its complex conjugate, that will give you the probability. And that means you will have to take the thing that we just calculated, you know, the alpha into 1 over gamma. That will be this term with m's. And then you also need to plug it into this term here, but with n's, the letter n for nut instead of m for mother. And you need to calculate it all. But you don't really need to bother with all of that because we know what the answer is going to be. If that angle is theta, we've already worked this out some time ago. So you can actually do this maths It is horrendous, but at the end of the day, what you should find is that the probability, if you prepare it in state M and you measure it along the coordinate n, the probability of it giving you an up will of course be cos squared theta over 2, which is one of the things we identified at the beginning or near the beginning of this video.